right, next up we're going to take a look at problems 24 through 30. So a slightly smaller set this time. So we're going to go into geometry. Here's where you're going to find the problems and the hints and tips and so on yourself. Go up to classwork. Go over to, and always get this stuff out of the classwork folder. Every time I post it in classwork, it'll show up in stream as well. But sometimes I'll make edits afterwards, and the edits will show up in classwork, but sometimes they don't show up in the stream. So if you want the most up-to-date version, go to the classwork. All right, so here we are in Unit 1, Pythagorean Theorem, problems 24 to 30. So we'll open that up. I'm going to get that in its own window. I'm going to go back here, and I'm going to open up the actual problem set. There it is. Okay, I'll open that up in its own window. All right. I'll come down here. Make this just a little bigger so it fills up the screen a little better. We're going to scroll down to problem 24. Okay, there's a lot to read here, and you do need to read it. But I'm going to give you the quick overview. So Una buys some candles. She lights all the candles at 7:30. So here's our timeline, 7:30, and they're all 10 inches long at 7:30 when she lights them. Some of the candles are cheap and they burn up faster. Some of the candles are more expensive and they burn slower. So the cheap candles are going to completely burn up in 3 hours. So here by 10:30, they're burn up. The better candles make it all the way down here to 12:30, 5 hours. At some point during the evening, someone looks over and they notice that the good candles are all twice as tall as the cheap candles. And the question is, what time was that observation made? So there's two ways that you could kind of go about working on this. One is you copy down this timeline here, and you just sort of start pointing out, well, if at 7:30 they are 10 inches and at 10:30 they're 0 inches and it's burning at a constant rate, that's 3 hours. So halfway they should be at 5 inches. So the cheap candles at 7:30, half of 3 hours is an hour and a half, so that's 8:30, 9 o'clock. So right around 9 o'clock, those candles are going to be at 5 inches. Okay. And then we look at the big candles. Well, they've got 5 hours to burn up, so it's going to take 2.5 hours for them to get to 5 inches. So that's 7:30, 8:30, 9:30, 10 o'clock. So at 10, those candles are at 5 inches. And then you can say, well, okay, if they're at 5 inches, so when are they at 2.5? So what time is halfway between 7:30 and 10 o'clock? Or what time is halfway? Or you can work out some other fraction if you want, but you're just sort of whittling down to find out where each candle is at different times. And you should be able, using that process, to kind of narrow down the window to, a 10 or 15 minute window when the candles have to be, at that, good candles twice as tall as the small candles. The other thing you could do is you could write an equation for it. And using that, you can get a very precise answer. I rounded mine off to the 100th of a second. Okay? So the very precise answer to set up the equation involves using the equation rate times time equals distance. And you're thinking of like the distance is the distance that the candles have burned down. Rate is the rate at which the candles are burning. And the time is the time since they started. So, for example, if the expensive candles take 5 hours to burn through 10 inches of candle, then that's 10 inches per 5 hours, which reduces to 2 inches per hour. So there's their rate. The cheap candles, well, they're 10 inches per 3 hours. So that's 10/3 inches per hour, right? Which you could turn into a decimal, but don't for your calculations because it's going to cause you trouble and make it inaccurate. So keep the fractions as much as you may hate them. So, of course, the kind of whittling away method is good, but the the equation method is better. I highly encourage you to try it out. If you try something out and you're not sure about it, it's not seeming to be working, talk with me about it. I'm more than happy to answer your questions. All right, problem 25. It's again plot a couple points, plot a third point, show the third point is equidistant from the first two, and then describe all such points that are equidistant from the first two. We've been through this before. I'm going to give you, so there's the two original points. There's point P up here. All right, go back to problem 15, where I kind of gave you some tips on how to do that. And then down here, you can click here for a description of what to call, or it's perpendicular bisector is what it is. But you'll want to click on the description and take a look at it. I'm sure it'll just confirm what you kind of already see when you plot all those points. Okay, number 26. Again, it's another find 2 points on the y-axis. So we've done a bunch of these where there's a line or an axis, and you're asked to find 2 points that are a certain distance from a given point, but on that line. And hopefully you've been drawing these sort of triangle-like shapes, and so I think most of them have been up-down. This one is different, and it's different because the coordinates for these points aren't whole numbers. So as of yet, it's always been whole number coordinates, and it's relied on us using right triangles that have whole number lengths for sides. So those are called Pythagorean triples, by the way. This one isn't like that. The coordinates you've got to find are not whole numbers. So, but you still use Pythagorean theorem to find them. All right, number 27. Let's see, asks you to find 2 lattice points. So the definition of a lattice point, it gives it. But like if you're drawing on a grid, the lattice point is the points where the grid lines meet, or any whole numbered point like 3, 4, or 8, 7, -2, 5. Or it's basically anywhere where the grid lines cross, lattice points. So here, and again, this stupid grid fades away with a scan, but I plotted point A, and I plotted 4 points that are square root of 13 away from A. So you're supposed to find lattice points that are square root of 13 away from each other. Now, square root of 13 is about 3.61 approximately, but not exactly. And so none of these points is lattice points, are lattice points. They're all in between grid lines in some way or another. But what you can do is you kind of look how long these lines are and just sort of kind of fish around in this area and see if you can find a point or several points that are square root of 13 away, and you can just verify using Pythagorean theorem from that central point. And I'd recommend that you find several of them and kind of look for a pattern, because that pattern should be able to help you answer the second question about whether you can find lattice points that are square root of 15 apart, or if it's possible to construct a square whose area is 18 by connecting 4 lattice points. Hint, the answer is yes, but you have to draw the square and figure out how. All right, next up we have 28. The first part of 28 is just a whole bunch of vocab. If you go over here, where I mentioned that's a whole bunch of vocab, there's a video I posted that goes over a lot of that vocab, so you can read what's there. You can look in the glossary at the definitions, and you can check out this video for some more of the vocab. But down here they talk about blah, 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 blah. What can be said about the 2 non-right angles in a right triangle? And if you go back over here, if you hover over this area here, there's some information about angle measures in here, information about angle measures in here. So if you think about it, if these 3 angles added together equal 180, because the inside angles of a triangle add up to 180, and I know one of them is 90, what do the other 2 add up to? All right, 2 more real quick. Number 29. So you're supposed to, plot P as AB. What does that mean? And R as negative BA, and then draw this diagram. So what does that mean exactly? So here's what we're going to do. I'm going to give you different values for A and B. So in this first one, A and B are 3 and 2. Here, they're 4 and 3. Down here, they're 7 and 5. Over here, they're 5 and 3. And you just got to copy these diagrams down. Again, the grid lines get a little washed out, but you can recreate the drawings. And notice that these two triangles are congruent. So I have angle 1 and angle 2, angle 1 and angle 2. All right? And so across the bottom I have angle 2 and angle 1, and I have a leftover angle here. The three angles across the bottom, they all form a straight angle, and we know what the measure of a straight angle is if we go back and watch that video. And we know what angles 1 and 2 add up to because we just talked about it in the previous problem. So you should be able to subtract their measures to find out what the measure of the middle one is. Right? Go ahead and find the slopes of RQ and QP for each of these, and then kind of look at how those numbers work out. For a little extra help here, negative reciprocals is a term they use. There's a definition in the glossary in the back, but this video I think gives a pretty detailed explanation of it and shows some of the more peculiar cases that come up that might kind of throw you for a loop. And it's real short, it's only a couple minutes long. If you need to review slope, go ahead and click on this video. It's just a quick review of slope. Last, problem 30, we're supposed to draw an equilateral hexagon where all the side lengths are square root of 13 units long. Well, if you go back up a couple problems, you've already drawn a segment that's square root of 13 long. So all you have to do now is just put 6 of them together in a path that leads you back where you started, and that'll make a hexagon that has all side lengths of square root of 13. And you'll be done. As usual, if you try something out and it doesn't seem right or you have questions about it, please come and ask. I'll be more than happy to help you out with it. All right? Good luck.